One, through properties of real numbers. One of the most, I think, important things in mathematics is understanding groups of numbers, okay, or what we like to call sets, okay? So this isn't here. I didn't put this down there, but let's write down a definition of what we call a set, okay? A set is a grouping or collection of objects. Okay? And then I'm going to write another word here called subset, which is a smaller collection of objects that came from a larger set. Okay, so the way that I think about this, I think the easiest thing for you guys is to just view this classroom, the people that are in this classroom. So there's there's 9 of us right now. Okay, so let's say that us 9 are a set. We're a collection of objects, right? Just in this case, people or the object. Okay. If I look at this side of the room, these 5 people, okay, these 5 people, would they be a smaller collection of the class? So you guys would be a subset, okay? You 3 over here would also be another subset, okay? And we can pair up, triple up, quadruple up, however many we want to, and say that, you know, this smaller group of people is a subset of the larger group of the class, okay? If I look at the school population and call the school population a set, then freshmen are a subset. Juniors are a subset. Seniors subset. Sophomore subset. Okay, if we include the teachers in the population, they would be a subset. Does that kind of make sense? Okay. Our number system is that way. Okay, our number system are sets of objects. Objects are just numbers. Does that make sense? Okay. It's going to be very important because of a lot of our rules later on will be rules that are, they'll incorporate, they'll say that this rule only works for integers, or this rule only works for irrational numbers, or only works for your natural numbers, or it tells you that a variable has to take hold of maybe just a natural number, or it's only allowed to be a natural number. And if we don't know what those number sets are, then we can't use those rules in the appropriate manner, okay, and they can get us into trouble, okay? So our natural number, I'm going to give you ways of remembering all of these things, okay? And if you can remember the first 2, then that's going to help you remember the third one, okay? And then the last 2 kind of link together as well. But natural numbers, let's think about this. I walk into the classroom, and my goal, my task is to count everybody in this classroom. What number would you naturally start with if you're counting somebody? 1, right? Okay. So your natural numbers, because it's natural to start at 1. I would not walk into this classroom and point at Austin and say 0, and then go to Jenna and go 1 and keep going all the way through until I got to 8, right? Because if I started at 0 and got to 8, that would actually be all 9 of us, right? Okay. But that doesn't make a whole lot of sense. You know, I want to start at 1. That's natural, okay? So your natural numbers start at 1. They go to 2. They go to 3. Go to 4. And they can keep that pattern. So these ellipses tell us they keep that pattern on to infinity, okay? Sometimes, especially in the younger grades, they called those counting numbers, because that's what you're doing, okay? When I put those little curly braces on there, that's just the notation for sets, okay? It just the way we do things. I don't know how big of a deal it's going to be in this class, But if I don't want to write natural numbers down a lot, okay? So what they will do is that they will abbreviate that with an N that has like, I did a crappy job of writing that. Let me do this. Obviously, you can put this anywhere you want to in your notes, but natural numbers, a lot of times they use a capital N, but that little cross brace is like a double line. So that's what we call our natural numbers. Okay? Now, the next set is our whole numbers. Okay? And I always remember them in this order because if I start with my natural numbers, the whole numbers, they are the exact same thing, but they include one number that is not up there. Does anybody know what number the whole numbers include that is not in the natural numbers? 0. Okay? So our whole numbers, and there's a couple different ways you're going to see whole numbers written as like an abbreviation, but they do it this way. And they'll either put a 0 up there or they'll put a 0 down there. Okay? I'm going to put it down at the bottom. But our whole numbers are our natural numbers, but they start at 0, they go to 1, they go to 2, they go to 3, they go to 4, and go all the way to infinity. Not much different. It's the same exact list except for the inclusion of a 0. Because some rules will need us to be able to use 0, and some rules will need us not to include 0. So some rules it makes sense to use natural numbers, some rules it makes sense to use the whole numbers. And we'll get to that later in the year and when those things come up. Okay? Now integers, this is kind of different. Integers is a Z like that, and that's the one that's kind of most common. So of the abbreviations or the labels of these sets, that one is the one that is the most commonly used and is going to be asked of you over the year. So capital Z is our integers. Doesn't make a whole lot of sense on why they use a Z, right? But just the way it is. Now, what types of numbers? So I've got 0, 1, 2, 3, 4, 5, 6, 7, 8, all the way to infinity. What kind of numbers are we missing up there? You included 0 previously. What are some other numbers that we're missing? Okay, so negative numbers are the ones we're missing first, okay? You're right about the fraction stuff, but we'll get to that. But your integers are your whole numbers and their opposites. So I'm going to start in the middle here, and I'll write out that list. But then they go in this direction as well to negative infinity. Give myself enough room. Okay, so natural numbers, I remember by the word natural. What if I'm going to start counting somebody, what number do I naturally start at? Okay, or counting a list of things or a set of things. Whole numbers, the way I remember whole numbers is that they are your natural numbers with 0. And the way I remember, so people get these two confused. Okay, they mix them up. But doesn't whole numbers have that O in them in the word? Right? So an O looks a lot like a 0, right? So that's how I link them and remember whole numbers is the list with the 0 in it, and natural numbers does not have a 0 in it. Does that make sense? Okay, so I think creating little tricks like that to help you remember things are useful. Integers then, I just remember integers are my whole numbers and their opposites. Okay. Now rational numbers are not written as a list because there's no real particular order to the list, and the list is infinite. So what we do with the rational numbers, the root word for rational is ratio, right? Okay. Ratio, by definition, is a comparison of two numbers through division. So soon you get your fractions, right? Now, you can remember it that way. Ratio is a fraction, but I always remember when I was in school, rational to me sounds like fractional. Does that make sense? So rational, fractional. So rational means these are my fractions, okay? These are my numbers, and we write it this way. They are the values A over B, and then we say where A and B belong to your integers. Okay, that little E right there that I just wrote after that B is the word or is the symbol for is elements of, or we can read it as belongs to. Okay, so rational numbers are anything that can be written as A over B, where A and B are integers. Okay, now what number are you not allowed to divide by ever? If I gave you any number and told you to divide it by something, what is that something you can never divide by? 0. Okay? So we got to make sure that even though A and B are integers, B is not allowed to be 0 because you get an undefined value when we do that. Okay? So what that does is that produces, like, so let's say A was 1 and B is 2. Divide them, I get 1 over 2, right? That's 1/2. That's my fraction. If A is 2 and B is 3, I get 2/3. So there's a fraction. It's one of my rational numbers. Does that make sense? Okay. And we have to write it that way because there's really no particular order. Because if you say, okay, well, I'm going to go from 1/2 to 2/3, which is in order. Okay. But now what if I go, 1/8? Where does that fall in that list? It's before the 1/2. So I got to put that in front. So it's just very messy to make a list. So we write it that way. Okay? Irrational numbers. I guess this isn't a big deal, but if you want an abbreviation that we use for these, rational numbers, we use a Q, like a little cursive Q. Does anybody know why? What word with fractions or division starts with a Q? Quotient. Okay. Now, irrational numbers is weird because you have our rationals, and then if something's not rational, it's irrational. So we call it the complement of the rationals. You don't really need to know that, but it's Q with a capital C, kind of as what we call a superscript there. Huh? What does it have eyes? Oh, that's just because when I started, I didn't put eyes in. I see what you're saying. I didn't draw eyes in there. Like that, right? Like that thing right there and that right there. No, those aren't. So that's my loop on my cue. Like, all right. So no, it's just cap Q. So irrational numbers are numbers that are not rational. Okay, numbers that are not rational. So basically we say they are numbers that cannot be expressed as A divided by B. So there are some numbers out there that you cannot write as a fraction. Okay? Everything that we have in that list so far, in all those lists, can be written as a fraction. If I think about the number 4, can I write that as 4 over 1? That's a fraction, right? Okay, and it's still 4. Anything in that rational list, 2 or 3, 5 or 7, 112 over 15. Those are all rational numbers. They can be written as a number divided by a number. There are some numbers that you cannot do that with. For instance, what's the number 1 irrational number that you guys have probably dealt with in the past? Nope. You eat them sometimes. Sometimes they're cherry, sometimes they're apple, sometimes they're pie. Okay? So pie, now it's not spelled the same way, but so examples of this, so an example of this would be pi, which we spell P-I. Okay? Now, I don't want to say most, all of your irrational numbers are going to be written with a symbol, okay? Because what irrational numbers do? Irrational numbers never end and they never repeat, okay? They never end and they never repeat. Right, so 1/3 never ends because it's 0.333333333, but it repeats, right? Okay, so pi 3.14, like 12915, whatever it is, that goes on forever, and it never repeats. Okay, it will never stop. You never see a pattern in it, that sort of thing. Okay. Some other ones that you guys are maybe familiar with are your square roots. Okay, so like square root of 2. Okay, that never ends and it never repeats. Square root of 3, square root of 5, square root of 7. Okay, square root of 4 though. Let me ask you that one. Square root of 4. Does anybody know what the square root of 4 is? It's 2, right? Does 2 end? Yeah, 2 is one of those other numbers up there, right? It's one of those other lists. Okay, so there are, when you have a perfect square under a radical, that's kind of a trick question almost on what group they belong to. You gotta simplify them. There are other numbers. There's a number called E, which we'll talk about later on when we start talking about finances. Or maybe you've even seen that in science. E is called the natural number, which is weird because there's a list of numbers called natural numbers, but this is a particular individual number we call a natural number. Sometimes it's called Napier's constant. It's a guy named Euler, or Euler, is how you spell his name, investigated and found this number. So the E is like in respect to him. But let's see. I think they wiped my computer clean and I lost a program. Yeah. Maybe I'll find it and re-download it. But I just wanted to show you, like if I type in pi into this program, it will put it out to like 1 million decimal places, and like you can recognize that there is no pattern to it. Okay. Usually when we type in pi on our calculators, it hits enter. Most of our calculators that we have access to are maybe so they go out to like 10 decimal places, 9 decimal places. Okay, but how do I know beyond that it doesn't just start showing that pattern again? Okay, the program that I have kind of explains that or expresses that. Something I've, when we talk about irrational numbers, I think it's kind of interesting. Let's say we take the alphabet and assign, like A is assigned the number 1, B is assigned 2, C 3, D 4, and so forth, all the way through 26, and 26 would be Z, right? What we can do is somewhere inside pi, as it's written out in its entirety, if I look for one of your names inside there, your name will show up somewhere. Does that make sense? Every book ever written, word for word, if we did that, think about this, every book ever written, word for word, every conversation you and I have ever had or ever will have, word for word, would be spelled out in pi somewhere. That's just how infinity works and how big infinity is. Does that kind of make sense? Okay. So I always say, think about like the biggest encyclopedia you could find. Word for word, somewhere, it exists in pi in its entirety. It's pretty crazy, ain't it? Your phone number is in pi somewhere. It is. But every irrational number is that way. Who found pi? One of the first documented places that pi is found is in the Bible. Talking about the fountain at the temple. But pi is simply, if you guys know what pi is, where it comes from? If you take any circle any circle you ever create, if it's a perfect, so now you draw it by hand, it's not going to happen. But any circle that you can create that is a perfect circle, and you're able to measure its diameter perfectly, if you divide its circumference, okay, which is the distance around, right, and you divide it by its diameter, okay, which is the largest width of the circle, right, okay, it goes through the center of the circle, that segment. If you divide those two numbers, no matter how big your circle is, it always works out to give you pi. So that's where they came up with and recognized that value. Okay, does that kind of make sense? Okay, so I'll just show you real quick with this. If I put in a circle here, I'll see here, get rid of these axes. All right, so that circle there, I have no idea how big that circle is. Don't really care. But I'm going to now create that line right there. And that line is between D and whatever that letter up there is that got covered up twice. That there. Okay, so let's see here. Let me hide some stuff. Would you agree that that's a circle and A is the center of the circle, so that line passing through is the diameter, right? Okay, so let's do this real quick. Let's take, I believe I can ask this thing to figure out circumference. So I can say circumference, and then it says conic, and my conic here is C, which is just this circle. So it's going to tell me the circumference of that circle, which is that number right there. Is that okay with everybody? Okay. Now I'm going to ask it to take, so G is the length of that segment right there. See how I clicked on that segment and highlighted G? So if I take A and we divide it by G, A, so circumference divided by G, which is the diameter, it gives me that number right there. Now I'm going to type in pi, and it gives me that number right there, and I'm going to go out to 15 decimal places. That's as far as this will let me go. Are those two numbers, the one I got through the calculation, the circumference divided by the diameter, is that exactly the same as pi? Now, if I do this, you might say, well, that just works for that circle. Do those numbers change at all? This number here and that number there, the diameter and the circumference change, but does their quotient of pi ever change? Okay, so that's changing from, so that one, and this is what we need to know about. See if I can get it to actually stop on one of those. Oh. Well, when I let go of my, there we go. So that number right there, that is a calculation. It was the circumference divided by the diameter. And what every calculator is doing, we don't have an understanding, we don't have any certainty on that number, okay? Because I don't know the number after. Does that make sense? Okay, so the way your calculator always works is that last number you see could be the value it should be, or it could be rounded up based on what the one behind it is. Does that make sense? Because this is the exact value. So when it goes out to 15 decimal places, so this is telling me that that number after this 4 should actually be a number less than 5, because this is the actual value of pi, which is telling me it's not. It should be rounded up. Because this is a calculation. This one here, yeah, this one here is a calculation. This one is not. This is a definition. Okay. But whenever you type something in your calculator, the last number that shows up, if your calculator expends all the decimal places that it has, I think it's like 9 or 10 decimal places, that last number you are uncertain of because you don't know what the number after it is supposed to be. Okay. If I know what the number after it is supposed to be, then obviously I don't need to round that one before it. So you never know if that last decimal. So when I do, give me a number. Somebody give me a number off the top of your head. 72. Now give me another number. Okay. So when I divide those, I don't know if that should be a 2, okay, or it should have been a 1, okay, because I don't know the number that's coming after it. I don't know this number over here in this spot right here, which would have told me to to round that 2 up, or if that number is less than 5 and it told me to keep that 2 a 2. Does that make sense? Okay. So those are just little things that we talk about in this class about our technology might be maybe misleading if we don't understand those things in the background. All right. So those are our numbers. So let's talk about our numbers. All right. So what happens is these are sets. These are groups. So what I want to do is I want to draw a picture here. Okay. When you draw this picture, the scale, don't like the first bubble we make, don't make it the entire rectangle, okay? Because you're going to run out of room and it's going to be messy. So I will try to keep this as to scale for you as possible, okay? But our smallest set of numbers up there, even though they all have an infinite number of things in them, the smallest set is our natural numbers, okay? Think about why. Even though natural and whole numbers both have infinite numbers in them, infinite objects. Doesn't whole numbers have 0 and natural numbers doesn't? So whole numbers has one more thing in it, one more object. So natural numbers are our smallest set of values. So that's weird. Hold on a second, my pen just fell apart. Okay, so we've got so I'm going to draw a little bubble here, and I'll put natural numbers in it. Okay. So anything that I put in that bubble, so eventually I'll put like a dot in there. That dot represents what we call a natural number. So it comes from that list of 1, 2, 3, 4, 5, 6, 7, all the way to infinity. Okay. So then, around that, so that is a set. Around that, I'm going to put it a whole other circle. And in that one, I'm going to write the phrase whole numbers. Okay, so what that does, what that image does is now tells me that if I look at the biggest set up there, my whole numbers is my biggest set. Does that make sense? If you pick numbers that are in your whole numbers, okay, they may also be natural numbers, because natural numbers are what we call a subset of our whole numbers. So give me a number. Somebody give me a number that does not have a decimal on it. Just give me a 12. Okay, so let's go 12. So 12, I would put maybe right there. Okay, so 12, because of its location, it's inside both circles, isn't it? So we would say 12 is a natural number, but it's also a whole number. Does that make sense? Okay. What about 0? Should 0 go in this natural number list? No. So 0 would maybe be right there. So 0, it's a whole number, but it's not a natural number. Does that make sense? Okay. So what's the next list of numbers that was bigger than the whole numbers? They were your integers. So I'm going to make a bubble for my integers. Those are my integers. Okay. Now think about this. I've got 12 and I've got 0 in the correct spots. Are they inside the bubble of integers? So 12 and 0 are integers, right? What is a number that would not be a whole number or a natural number, but would be an integer? Negative what? Negative 1. Okay. Negative 1 is an integer, but it's not a whole number and it's not a natural number. Okay. We cool that? Next list of numbers. Rational, right? So I'll make another bubble. So everything that we have out there, every one of those specific examples of -1, 0, and 12, they are inside the rational group, right? Okay, so they are rational. So that must mean that 12 can be written as a ratio, 12 over 1. And that's the idea, that every number that we have, every whole number written over 1 is a rational number. But what is a rational number that is not an integer, is not a whole number, is not a natural number? 1/2, 2/3, any fraction you want to come up with could be one. Okay, does that make sense? So what I'm saying here is, like if I compare the groups, the stuff here that I can color yellow here, those would be like all the rational numbers that are not like 5 over 1 or 7 over 1 or 12 over 1, right? Everything in the yellow would be like a 1/2 or a 2/3 or a 4/5 or something like that. Okay. Now, our irrational number, think about irrational and rational numbers. It says rational numbers are A over B. Irrational numbers are things that cannot be written as A over B, right? So you got something that exists, and basically then you have like its counter object, okay? It's complete opposite almost. Does that make sense? So there can't be any overlap between irrationals and rationals. So what we do is we create a bubble here, and this is our irrational list. It's hard to write this way. I'm not going to do it. Let's write it this way. So irrationals. And again, those are your numbers like pi, radical 2, radical 3, e. Okay. So what our rationals do is they fill in most of our number line. They fill in a lot of our number line. But when we fill in our number line with our rationals, we have gaps. Okay? And those gaps are pi, radical 2, radical 3, radical 5, those kinds of numbers. Okay? So in order to fill in those gaps, we combine the rational numbers, we combine the irrational numbers, we throw them all together, and then what that creates is a continuous number line that has no gaps, no holes, nothing like that. And that continuous number line, does anybody know what it's called? Starts with an R. Real numbers. Okay. So the fact that we get things that are called real numbers makes us think that there might be numbers that are fake, right? There are things that we call imaginary numbers eventually, but they're not fake. They're legit. There's kind of a misnomer. But real numbers is the collection of all of these numbers together in one group. Okay? So that's our real number line. So when I ask you something like this, when I say determine like what kind of number is 2/3, when I ask that question, I need to find the smallest subset that belongs to. Okay? So I start on my outside in, or outside working in, and I start looking down, okay, where does it belong? 2/3 is here, right? It's not an integer, it's a rational number, correct? So when I locate 2/3 as a rational number, 2/3 should go there, right? And now when they ask me to classify it, we're going to say it is rational because it's part of that group, but it is also real because because rationals are a subgroup of your reals. Is that okay? Somebody give me another number. Give me a number that has no decimal and 24. Okay. So 24. So I'm going to look for, where should 24 go? 24 should go about right here, right? Should be a natural number. You guys agree with that? Okay. It's one of my counting numbers essentially. So 24, this is the way we're going to do this. 24. The innermost circle it belongs to, or set it belongs to, is the natural numbers. But the natural, if it's natural, it automatically is a whole number. If it's a whole number, it's automatically an integer. And if it's an integer, it's automatically rational. And if it's rational, it's automatically real. Does that kind of make sense? So once you find kind of its home, where it belongs, it is then also able to be classified as the things that are around it, or the sets that are bigger than it, or the sets that contain it. Does that kind of make sense? Okay. What about pi? If I say pi is irrational, right? So if it's irrational, irrationals are part of this big blue box, so it is also real. So whenever you identify something as irrational, you'll also be able to say it's automatically real. All of these, no matter where I put a number up there, it's automatically going to be real. Okay. You guys remember talking about that in other classes before? A little bit? Okay. You lying to me? All right, I'm gonna stop there for today.